Hello, everyone. My name is Zamani. I'm hosting this talk. It's my pleasure to host Carsten. He is an assistant professor at, he's now professor at the University of Tübingen. And he's working on information retrieval and natural language processing. We'll focus on medical domains like improving patient safety, individual health, and quality of medical care. Before his current appointment, he was an assistant professor at Brown University, very close to us. And I was just telling him that I'm really sad that he left our proximity. He has been incredibly active in the research community. He has published over 100 articles in CS conferences like CIIR, ACL, ICLR, and also clinical journals like Nature Digital Medicine and the others. And he has been also incredibly successful in terms of project grant fundings and things like that in the US and also in Europe, for example, from Swiss National Science Foundation, NSF, DARPA, Google, Amazon, Microsoft, and the rest. So without further ado, I'd like to invite Carsten to talk to us about uncertainty in IR, which seems like a very, very interesting topic. Please.
Perfect. Thank you so much. I hope you can see my slides, hear me okay. I'm very excited to be here, or not be here, I guess, and talk to you guys. So as you can see from my slides, I'm still in this split brain situation between Brown and Tübingen, with most of my lab still being in Providence, but so we're working on it over the coming years. And my clicker almost wants to do it. Okay, Ahmed already introduced myself, so we can skip over this. Oh, here we go. So these are all the folks, some of whom you may know from conferences. So these are all the folks who work on all these fun projects we're talking about. And just as a very quick bit of scene setting of what has been going on in the past few years, the stuff that we are interested in. So I guess on the right-hand side here, so largely the things we do fall into these IR NLP flavored applications. So I would say roughly half of the things we do are really basic scientific sort of CS conference paper style works. And then we have a good chunk of applied work that really targets typically clinical or otherwise health related problems. And they don't go more into either medical informatics or clinical journals. On the method side here on the left, we're interested, like many other folks at the moment, in dense retrieval, or more generally neural retrieval architectures, I guess. Then there's this topical complex here of explainable information retrieval and uncertainty, which sort of goes hand in hand. So having these models shed some light onto their inner workings, and this is also what we're going to talk about today. We've been doing quite a bit of work on grounding and manifold learning in language modeling. So trying to sort of see what these models really encode, whether some of these either geometric or conceptual properties are desirable, and whether we want to sort of enforce some other properties here. And then there's been a bit of work on conditional text generation where we try to get away from this one-size-fits-all kind of style of translating, summarizing, or simplification, and instead try to do this with a concrete recipient in mind. So try to summarize a patient record, but for a physician of a specific specialization, or maybe for a user with a specific mix of topical interests, right? So summarize this newspaper article, don't just make it short, but make it short for me. And then clinical decision support, either for suggesting the right diagnoses or maybe treatments for a particular patient in a certain context and situation, is another big topic that we do some work on. But today we're going to talk about explainability and uncertainty. I want to spend a very brief amount of time on where I see explainability right now, just because there's sort of is a bit subjective, I guess, and a lot of people mean lots of things when they talk about explainability. And then I want to go to what I sometimes think of as the poor man's version of explainability, which is these uncertainty estimates. So we want to see how we can get uncertainty estimates out of arbitrary, let's say, IR infrastructures, how to then use this to first measure and hopefully improve fairness downstream in rankings. And then hopefully we'll have plenty of time to discuss. If you have any questions anytime throughout, just interrupt me. I carved out, I think, enough time at the end for discussions, but also anytime throughout, just let me know and we can chat then. All right. So explainability for these models. So I think the first thing that's very interesting to distinguish always is, are we explaining models in general? And this is usually your SHAP values, if you've seen this, right? So what makes the model tick? And this is basically trying to reveal some of the inner workings of these models, but in general. So this could be the coefficients of a linear regression model, or this could be SHAP values or something like that, that say, in general, the model will react to the following features or the following properties this strongly. So the model is mostly driven by blood pressure or by term overlap or what have you. And then the alternative interpretation of explainability is this instance-driven way of explaining, right? So the model takes a concrete data point, so an image, and says yes, no, dog or cat in the image. And I want to explain why do I get this particular decision for this particular data point. So not in general, the model pays attention to blood pressure, but for this particular patient here, the diagnosis was recommended because of the combination of age and maybe some genetic marker that we noticed in the patient. And then, and this is where things get exciting, we have the user coming in, right? So the person who issued the query, who created the data point. And I think there we have this very interesting distinction between maybe expert users, what that I tried to sketch out on the left here, and lay people on the right, who may have very different degrees of understanding of how a system like this one might work, right? So search engineer versus user maybe. And who might also have very different degrees of general statistical knowledge. So can I come with p-values or confidence intervals, or should I talk in more broadly accessible metaphors? All right, and then finally, this gives us something like this little matrix here. And I think it's really important in designing these transparent systems to think about whom am I explaining this to, right? So not just here's an explanation, I'll be happy, job done, but really to think about, am I talking about decision level properties, and I'm talking to experts. So that's sort of a debugging kind of use case where I really want to make sure that for my individual test cases, I understand instance by instance why the model performs the way it does. If I try to explain to experts on the system level, I probably look at purchasing decisions. So do I use this software or that software, or maybe really strategic decision making. Down here, we have our typical system users, right? So I want to probably explain decision level behavior of the model and do it in such a way that your run-of-the-mill web searcher, for example, might be able to follow. And then down here, you have maybe the media, right? So try to explain system-wide to a lay audience. And this is maybe what we've been seeing now about ChatGPT in the last few months, I guess, right? So now suddenly everyone has an interest and wants to, in broad strokes, understand what's going on. Okay, so with this in mind, I'm not going to give you concrete explanations why this data point, why that, but we're going to go for our somewhat more affordable version of explanations, which is these uncertainty estimates. And we're going to force these models to tell us how certain they are in certain outputs. And I'm going to take you on a bit of a journey through a bunch of papers that have appeared and are hopefully going to appear. So the last one that we'll talk about today is really under review right now. So this is sort of the press, or still in press. And we're going to start 2 years ago at CIIR, where Dan Cohen and some others looked at uncertainty estimation, and especially from an efficiency angle. Okay, so and I'm going to talk you through a little scenario before we dive in here. So assume we have two ranking models, right? So so we have this model A and model B, left and right, and they take documents 1 through n and put them in an ordering. And now assume here that the ordering is exactly the same, right? So we have two different systems. We have the same documents being ranked. They are in the same rank order, and that would mean that under most metrics that we commonly use, these systems would get the same scores. Right? So now we can say, okay, these systems are completely equivalent. In a track competition or what have you, these systems would score the same. But if we as search engineers and maybe also users of search systems think about this, probably a system such as model B has interesting properties here, right? So if everything is squashed into a very narrow range of the score scale, that's less informative than this model B here, where I can see that the first two documents might lie really closely by one another, and then I have a whole lot of gap in the score range before the third document arrives, and so on, right? So using the available scale of the scores fully might give us more expressiveness in these models, right? So that would be great to have that. And that might give us something that we can play with here. Okay, so what we try to do here is get close to this ideal setting. So we want to perform the same experiment many times, measure outcomes, and now talk about a distribution, right? So instead of saying I have a point estimate, I have a single retrieval model score, I ideally want to have two distributions for two documents, the red one and the blue one here. And I want to see that even though the means are maybe similar, the uncertain or the variance here is very differently tight, right? So where the blue model might be a bit arbitrary on whether the mean is really here, the red model is pretty certain. Okay, so this is going to be the goal for today to get there. In order to get there, we'll have to deal with two little challenges. First of all, we have a deterministic model. That's not great, right? So if I run this model 100 times, I get 100 times the same number. That's not a nice distribution. And then the second problem is that our forward pass through a modern retrieval model is somewhat expensive. I'm saying somewhat because, of course, it's cheap enough that we can run it at inference time, but it's maybe not a great idea to run it 100 times. So we want to try and see what we can do with both of these problems. Okay, for the first one here, we're going to use a technique that's called MonteCarlo Dropout that over the last few years has seen some popularity. But I want to quickly talk you through it just to make sure that we're all on the same page here. So we all know dropout for model training, right? So where we randomly drop out some of the inputs and force the model to deal with basically controlled degrees of random missingness. And MonteCarlo Dropout here uses the same idea, but for the neurons of the network, right? So we have a small random chance that this neuron here might be blocked out, and any path through this neuron is not available for this particular run, right? And now, basically, for the same inputs, I get, if I do multiple iterations of this, I get different outputs just because different paths through this network are not available anymore. So I do this at inference time. Okay, so this now gets me from a deterministic model to something that produces a range of scores because I withhold, if you will, different parts of the input, right? So different aspects of the input. If you think about your typical maybe transformer-based ranker, and if I withhold certain neurons and certain paths throughout, this will randomly withhold pieces of information of the document and thereby produce this score range. So if we do this, this is great. But now we have this little problem of computational complexity. So on CPU, you'll have something like 25 milliseconds for your conventional BERT pass. Even if you engineer this a bit, this is not great news if you afford yourselves 30 to 40 milliseconds total for ranking activity. And this is something that we usually see in commercial web search engines. So you'll have 30 to 40 milliseconds before, with network delay, you need to make your decision. So even 2 Monte Carlo runs would be borderline, definitely not 3. And the distribution of 2 or 3 data points is not fun. Okay, so we'll have to have a tiny bit more engineering here in order to get to our dream of a proper score distribution for a pair of query and document. And for that, we are drawing on this ICML paper from 2.5 years ago that talks about being a little bit Bayesian. And being a little bit Bayesian is something that really helps us here. So this paper, the bottom line of this paper that also came from Tübingen, funnily enough, was that if you reason over the final layers of your model, so basically repeat the final layers of your model with this MonteCarlo Dropout, you get something that's very close to the behavior of the full model. And so that's what we're going to do. We're going to run the first part of our models, so some bird or this nice KNRM pipeline here exactly once. Snapshot the inputs at this point, and only use the last 1 or 2 layers now in this MonteCarlo Dropout fashion to get our stochasticity in here and to be able to have score distributions rather than point estimates. And if we now do that, now we get really, really fast. So now we get less than a microsecond for 100 bird samples, for example, just because all we do is run only the fully connected layer or layers at the end multiple times. Okay, so that's great. Now we have our problems taken care of. And we'll get to a situation like this. Single document and query pair goes into our network with our MonteCarlo Dropout. We do this 100 times. We have a distribution of scores, and we get to a situation that looks something like this. So now we have our documents, again, at the different ranks here. We are going to rank by the mean rather than also of our distribution, rather than by the single point estimate that we had before. And we often see a picture like this. And this was somewhat counterintuitive. So Dan came with this at some point, and we were surprised to see this, that for a large number of queries, the top ranks will not just have high means, but also very, very tight confidence intervals, so very tight variances. And then at the lower ranks, not just is your mean lower, but also your distribution tends to get wider and wider. And this is an interesting property, right? So you go from highly relevant and pretty certain documents to less relevant and also more arbitrary ranks down here. Right? So we'll use these properties later in the second part of this talk. But for now, let's assume that we have this. We have a new way of ranking, and we want to see whether in doing this we are breaking anything. To do that, we designed a bunch of experiments here. We're using 2 models, convolutional KNRM and this BERT model. And we have three data sets here: MSMarco, Track Deep Learning 2019, and Robusto4. And due to Robusto4's somewhat smaller size here, we don't train on this one. So we have 2 conditions on which we train on these larger data sets. And this one here, we only use for evaluation. So here we train, I believe, on MSMarco and then evaluate on Robusto4. Okay, so here's the big bad table, and here's where to look. In introducing this MonteCarlo Dropout based little Bayesian version of the models, do we break search? And the good answer is we don't really. So we're showing you the deltas here to the basic version of the model, and you see that sometimes we win a percentage point, and sometimes we lose a percentage point, but by and large, these deltas are pretty small, and if you were to sum this up, you get somewhere close by 0, right? So it's really just the point estimate and the mean of the distribution will usually give you something that's pretty comparable. So that's great. So we're allowed to do this. It doesn't cost us much more time, and it doesn't break search, right? So we're not now suddenly many percentage points worse than we were before. So that's really great. So we got almost something out of nothing, which is always good in our quest for the free lunch. So next we're going to look at score calibration. So do these scores that we get out of the model look like probabilities? So that would be a really nice property. If we had something and it had a score of 0.5, would that give us, would that correspond to 50% likelihood of relevance, right? Which is far from the case for many models. If you think about BM25 with just random numeric scores, that doesn't have that property. And again, here we see, so here we are tracking the calibration error, so the distance that you are away from proper behavior as probability scores. And we can see that this calibration error falls pretty dramatically for all model pairs, except this one condition here where it's pretty comparable. So that was great to see. And then finally, as sort of the capstone to this paper, we were trying to make now use of this uncertainty information, right? So far, we said, okay, you can get uncertainty, and that would be great. So you can now expose this to your searcher and say, well, look here, we are 50% certain about this this result here, but the next one really we're not so sure. This might be equally relevant as any of the following ones. And so here now we try to use this uncertainty information as a feature in a cutoff prediction task. So here the idea is that we want to not just rank documents and bring them into this long string of documents here where I indicate factual relevance in green. But also we want to tell, given a concrete ranking, we want to tell the reader where to stop. Right? So where do you likely start mostly wasting time in reading further, and where's the majority of the juicy, interesting, relevant documents. Right, and there as well. So now instead of giving people just the score distribution, we will now have the uncertainty signal as well. And that's the addition of this feature really boosted performance in this task. So for all of these different pairs here, and this you should compare these guys to those guys. So the D's to the B's, so the deterministic to the Bayesian ones. You see that introduced a pretty consistent improvement in this task. So this is great, right? So now not only do we get this for virtually free, but it also helps us do something useful in ranking here or in cutoff prediction. All right, so that was the first chapter in this little journey. Now's a great moment to ask any questions if you have them so far.
Yes.
I assume these numbers on this slide too are the NDCG numbers.
This is a good question. I think this is actually
previous slide said,
because the cutoff prediction, I think, was measured in accuracy because there was a reference cutoff, I believe.
Oh, okay. Because obviously this would not be a good thing for math.
That's right. Okay. No, so if I'm not mistaken, this was a setting in which there was a reference cutoff that was determined according to some utility metric, and then this is a question of matching that cutoff. But I don't fully recall from the top of my head.
Hamed actually pulled your paper up. It says, so if I'd been patient, I could have just read over his shoulder. Apparently it's F1, so at the cutoff.
Okay. Awesome. Okay. I'm going to skip over this next part, but I want to very briefly tell you what happened next in the storyline, just so that you don't have to stay on the edge of your chairs. So in the next year, so last year at CIIR, we had a short paper that looked into the effects of uncertainty and different uncertainty distributions in especially medical search. And here what we tried to do was look at different query profiles that looked for medical conditions related to particular underserved groups, Native Americans, African Americans, men who have sex with men, so a bunch of profiles like that, that are disproportionately affected by certain conditions. And we were looking at the search performance, but also the uncertainty patterns here. And we basically use the confidence decay, so this pattern of high confidence at first, right? So very tight bounds, to lower confidence at the bottom in the shape of an exponential distribution, and we are using that as a performance predictor. So it's a sort of in air quotes performance predictor. It's a weak signal, but it gives you a first-hand or a first step prediction of will queries like these receive average performance under my model, right? So this is great. While it's not fully there as a performance predictor, it's great because it gives you an estimate of should I expect reliable performance for this type of queries under my model trained on the data that I have. And this is going to be a great motivating step for the next piece where we're going to talk about fairness in a moment. But so this was last year, and now we're getting to maybe this year's CIIR, we'll see, where together with Maria Heuss and Marta de Rijke, we've been looking into a continuation of this work in the realm of fairness. Now, let me show you the high-level intuition. I'm not going to spend much time on the math with this one here. We'll have, in this setting, we'll have a ranking from highest to lowest rank here, D1 through D4. And some of these documents now in this new setting will be protected documents, and others will be just general documents. And protected documents could be documents from a particular underserved news outlet. This could be documents that talk about protected groups, such as maybe women or African Americans or what have you, right? So the intuition is that if you don't pay attention to your ranking here, and if you don't do anything active about this, you may end up underrepresenting the green documents, right? So now, in an attempt to ensure fairness of exposure, what we want to try and do here is that among the top K of our ranked list, we want to have an even or at least controllable exposure of both the protected and the general documents. So, and what we'll be doing now is, and so this is what pretty much everyone in this realm does. So we'll now try and violate in a very controlled manner the probability ranking principle, and try and mess with our ranking in the re-ranking step such that we hopefully preserve utility, so don't break relevance, while improving fairness here, while balancing things out a bit. The first step here is going to be measuring our uncertainty again, and then rank by the distribution. So this is exactly what we did before, right? So for each query document pair, we do all this trick with our little Bayesian and our MonteCarlo Dropout. We get our distributions, so we fit this to a Gaussian, and we get our distributions here, and we rank by the mean. Now, in the next step, we're going to look at the confidence intervals of our distribution here. So, for example, 1 standard deviation. And now we'll start messing with things. So now we'll look at some parameter alpha that tells us how much we are messing, right? So the length of our errors here, relative to the standard deviation. So how many standard deviations I'm willing to downvote general documents, right? So these red ones here are going to have their scores, their ranking relevant scores decreased. And the green ones, the protected documents that I want to boost, they will have them increased by that same amount relative, again, to their own score distribution. And this may, like in cases like with documents 2 and 3 here, trigger even a swap in ranking. So after I've performed this operation, I want to go back in and I want to say, okay, now I rank by these adjusted scores. And I want to now hopefully have a more balanced ranking over this protected attribute. Now, this, of course, sacrifices maybe some utility for fairness, right? So I don't fully trust the point estimates or even the means of my distribution anymore, and I'm willing to sacrifice a bit. Now, why is this interesting? It's interesting because if I do this mostly for documents where I anyway wasn't so certain, so these things that are very flat and squashed out, then my risk of losing utility is somewhat lower. All right, so this idea is that I don't want to go into the top rank of the result list where my model is extremely certain that this is highly relevant and exchange that with rank 200, right? That would be a terrible idea. But here we want to say, oh, if we're anywhere in this murky area where things are more or less comparable, it's a bit arbitrary and not so clear that really document 3 should be in front of 5 and 4 and how they play together. There we are saying now we are willing to dare this swap, right? So the whole idea here is try to swap documents such that protected ones are being promoted, but only do that when the relevant scores are anyway comparable according to this game of modeling uncertainty in scores. Okay, so that's the idea here. Pretty simple scheme. There's many different ways in which you could play this. We did this now with this explicit switch of if you're a protected document, so you would have to estimate that in the real world. If you're a protected document, you'll receive that boost. If you're a general document, you'll receive that penalty, and then we'll reorder. You could do this slightly differently. It doesn't necessarily have to be played via this vehicle of the variance, but this sort of gives you a way of playing this game. We're going to look at a bunch of quick experiments in this space. The first one is going to look at the exact trade-off of fairness to utility. How does that behave? And we're going to use MS-Marco FAIR. So this is a subset of the MS-Marco data set. So 200, I believe, queries have been annotated for fairness, where we've looked at, I think, especially gender distributions, and where we wanted to have an explicit balance between male dominant and female dominant documents to have that broad representation there. And this, of course, only works for certain query types, right? So if you're asking for I don't know, President Biden's birthday, it really doesn't matter whether there's a male or female focus in the answers, because you're really just looking for this data. But I guess there's a whole bunch of fairness sensitive topics that you want to make sure you have a balanced representation of the real world and not just of the data set that you've trained on and learned on, that promotes the typical biases that we're all very familiar with. And then we're using a BERT-based retrieval model in order to make all of this happen. The very first thing that we wanted to start out with is a bit exploratory. So before even evaluating our model, we were going in and we wanted to see how much potential for swapping is there even. So horizontally, I'm plotting here the ranks of the result list. And then if I use 1 or 2 sigmas, so 1 or 2 standard deviations within which I swap, how many document candidates would there be to swap, right? And you see this general pattern that sort of follows from the distribution I've shown you before, right? So early ranked documents tend to have narrow bounds. Later ranked documents tend to have these wide, flat hill kind of distributions. And we see exactly this here with some local jiggle. It's typically the pattern that for the first few ranks, there are very few candidates for swapping with, just because they tend to be spaced out farther. And then as we go into the higher ranks, we very quickly, so I think this is around 4 or 5 rank, right? We have quite a few candidates to swap with. And of course, as I relax this even further, I get more candidates to swap with here. So we very quickly get into a realm of 10 or 20 possible swapping candidates if we're willing to go wider. For the rest of the experiments that I'm going to show you, we went with 1 standard deviation. So this seemed, from these 2 plots here, this seemed sufficient in order to see effects. Right? So if you never switch, of course, nothing happens. So we went with this one here to not muddy our relevance scores too much. Okay. So here is now the trade-off of fairness horizontally and NDCG utility vertically. And in blue, you see puffer. So this is the method that we put together here against a bunch of typically used fairness methods. And you see that we're getting a pretty good trade-off that arguably is one of the more interesting ones among these methods. When trying to trade or compare fairness for utility. Now, so the thing to observe here is that we are pretty far out already on the fairness scale. So in this particular data set, we can't claim that, oh, the world was terrible and everything is so unfair. So all the models already started out pretty fairly. But if you want to push this regime even further, some of these methods, the blue one among them, gives you a good way of balancing this out and doing this. I want to say a quick thing about the cost of swapping. So these methods come in two fundamental flavors. You have post-processing methods, such as ours, that take a score distribution and maybe some context and mess with the ranking, right? So they go in there and they say, okay, can I now massage the scores such that I get at hopefully not too much of a hit for utility, better fairness properties out of this. And you have in-processing methods that try to incorporate the fairness decision into the ranking step already, where you say, in order to be ranked highly, not only should you be topical as a document, but also you should be increasing fairness of the list, right? So these could be reinforcement learning based models, or these could be list-wise rankers that have some form of fairness incentive in order to rank things highly. And if we look at, so these are again for certain cutoffs here that we take in the NDCG range. We are and this alpha here is always the strength of fairness, regularization or enforcement, if you will. So all of these methods work a bit differently. So that's why these scores are not necessarily comparable here in the particular alphas. But so these are sort of the most effective alphas for the different methods. And if you look at the overhead cost, so unfair is just the general ranking. And then you have these different methods here where puffer performs very well in terms of computational overhead. So this is born out of the simplicity of the method, right? It's not really a surprise. We're not doing anything funky. We don't need any differentiation or anything. We don't need to mess with anything costly. So all we really do is go in there and say, reduce the score by up to a standard deviation times alpha to get your new score and then re-rank. So this is a dirt cheap operation, and we see that here, that this doesn't incorporate a huge overhead. And some of the other methods have costlier computational operations here. And then Coder here, for example, and ADV are in-processing methods. So they can't easily be quantified as re-ranking overhead just because they happen in the original ranking step. Okay. With this, I'm going to leave it at that for the time being. So leaving us plenty of time for discussion. And if we want to, we can even still jump into that little topic on measuring fairness of results and predicting query performance in a bit. But what I want to sort of leave you with as thoughts here and as sort of lessons learned from our little journey through fairness over the last going on 3 years now, is that uncertainty is a great vehicle for improving beyond just communicating to searchers. It's a great vehicle for communicating or for improving ranking performance, such as in cutoff prediction settings, or even for just giving robustness to these rankings by ranking by a distribution rather than a point estimate. You get better calibration out of your system, and this is something that I think many of us neglect. So I think we often stop at just taking our scores, ranking by them, throwing away the scores, never going back there, and calling it a day. I think in a strive for fairness and for transparency enabled interfaces, where we're going to have fewer and fewer opportunities to do this. So we'll probably in the future much more often try to expose these scores, and hopefully in the form of something that's interpretable, such a probability of relevance, something that behaves almost like a probability of relevance, to the searcher in some form of transparent interface where I can see what's my score distribution, what are my uncertainty bounds, what's going on here in the system, in order to properly interact with that and see what's going on. this is the part that I glossed over a bit. This is what we were talking about, detecting bias in these rankings, finding settings where if you're looking for congestive heart failure, you get much better results than for example, HIV and its connection to sexual preference. And now finally, we've been able to use it as a vehicle for not just measuring, but also improving fairness of these results, right? So as a heuristic for saying, where is my risk of losing utility smallest, so that I can boost fairness at hopefully no additional utility cost. All right, and with that, I'd like to thank you for your attention. I'm happy to take any questions that you might have.
Thank you, Carsten. Very interesting talk. Any questions from the audience here?
There's one in chat. Would you
Yeah.
see?
So I'll start with that one. There's a question in the chat saying, what is the main purpose of dropout?
Stop my share actually. In general or here for us? So I guess the general idea is to increase robustness of models, right? So if you use the traditional dropout in model training, you try to increase the robustness of your model by not always offering the same features reliably throughout. So now we are taking here, we're not looking at the training stage of the model, but at inference time. And here we use it as a hack to get stochasticity and variance sort of into the execution of the same query run against the same document many times. So now for us, the MonteCarlo dropout, so the idea of just withholding neurons and their connections throughout the path, they give us a range of different outcomes for the same experiment. In some ways, this makes sense. It's not just a technical hack. In some ways, this means let's withhold at the lowest level words, and let's withhold combinations of words or aspects of words that have propagated through the system for a few layers. And let's pretend they haven't been there. It's sort of a poor comparison because we have contextualized language models now. So some of the presence of each term might have propagated into other terms, into their encoding. But still, so we withhold some of the evidence from the document, which again makes sense because that same document might have been written with just slightly different terms or with a different focus on different aspects. So that's sort of what this simulates in some way. And would that still have been relevant, right? So that each of these MonteCarlo trials is basically saying, had we not included these words or this focus in the document, would that still have been relevant? Or was this a document that was just marginal to start with? And if you remove that one aspect, it really is not relevant at all anymore. And this is then expressed by this distribution. Does that make sense? And was that your question?
G, feel free to turn on your mic. Yes.
Yeah. Okay. Awesome.
So I ask a follow-up question. And another approach to deal with this is masking instead of dropout, right? Masking some tokens and documents in order to. And do you see any benefits in either of those?
I'm not sure that we deeply explored the difference. So I think we played around with it early on, and I now have to say I'm not sure I recall anymore. I think it was pretty similar, honestly, in behavior.
That makes sense. Questions?
So Carsten, this is James. I'm sort of shifting away from fairness when I look at your the uncertainty distributions you're showing. Do you think those might in some way be a tool for measuring whether systems are actually better than each other? If I instead of just my rank list and your rank list, and we want to declare, oh, I won by 0.03 or something like that. In fact, my distributions are wide, and I could just as easily have re-ranked half of my documents quite differently, not with fairness, just by where they ended up.
Mhm.
Would this be a way, could you imagine, speculate on how evaluation measures could maybe be changed with this in mind?
This is a fantastic idea. I have to admit, I never thought about this, but I think this would be a fantastic idea to also bring some jitter, if you will, almost into well-known collections and I guess well-researched collections where we may even have used very TF-IDF heavy baselines to do pre-ranking. So I think that would be very exciting to bring this into model comparison. I guess you could do this crudely on the document level by feeding really the identically modified representations into all models. But I guess on the but just forcing all models to produce uncertainty bounds in this way, and I think for most modern models we would be able to do this, just because the approach here is pretty generic. So as long as you have something that's neural network based, you should be able to get some way of getting this. And you could very well use even the shifting behavior, right? So not just what's the performance decay of your model, that would be one of them. That's what we used in that short paper that I sort of skimmed over today. So you could use that. Do you have a nice decay, or is that very abrupt and then looks different at the end? Or you could even say, what's your shifting behavior? So what's your number of allowable shifts, or what's your maybe even Kronecker delta or something like that. So the number of shifts that you're allowing yourself between these ranks. So I think that's super exciting.
Okay, well, maybe we'll have to collaborate on it.
Yeah, I'd love to.
Any other questions?
Hi, Carsten. I had a question. First of all, thanks for the great talk. So I was wondering if, I think a lot of what you were discussing were techniques at inference time. Are there also avenues to explore building this uncertainty estimation end-to-end, perhaps in the model training aspect as well, and then maybe like training the model to also optimize for the fairness constraints that you're talking about? Are those avenues that are worth exploring, and have you guys maybe speculated along those lines?
Mm-hmm. So this is something that goes more in the direction of, I think, some of the listwise learning models that we're seeing, where so pointwise this is really hard, right? So because pointwise you're just seeing the query in the document, and it's tricky to do much there, certainly when you want to look at fairness, right? So uncertainty, maybe you can still do something, but if you have listwise properties such as fairness, then it gets trickier. If you're looking at lists of documents, and I think there's a lot of very exciting work going on right now in that world, I think this is where you would go in, right? So this is where you would say, okay, now I see that my decay suddenly really takes off, right? Or things sort of peter off, and that's maybe where you would want to use that information at that point. I haven't seen anyone do anything in that realm. So there's quite a bit of uncertainty work being done right now. But I think most of it at the moment uses this for quantification of uncertainty and for communication. I don't think I know anyone or any works that use that at the training step. But I could imagine that, for example, even for things like, because so uncertainty, of course, comes from in multiple flavors, right? But really what we are after here is in many ways the epistemic uncertainty. So the uncertainty in your data, just because your data set was too biased, too small, too weirdly sampled, right? And I think this could be a great vehicle. So if you have these uncertainty estimates, use that for some form of biased sampling for your training data, right? If you're in some form of active learning scheme and you want to know what kinds of information should I really pay attention to, which kind of documents should recur more frequently, especially in a world where we train on 10% of a data set in retrieval, right? So we never really run our full collection. And if we don't do that, maybe we can use this for sort of detecting some of the weak or blind spots of our models and sample a more effective training set.
That's really interesting. Thanks for your answer.
Okay. This is Yuanche, and I have a question about because now everyone knows ChatGPT, so for conversational retrieval or something like that, I believe they are based on generative retrieval. Maybe they generate answers from the model's memory or something. So for this case, do you think the definition of uncertainty in IR changed, or do we need to consider more complex thing? Or I just want to know your points on this.
Yeah, so I'm very so this in some ways and less so on the uncertainty angle, but I think retrieval via generative models is something that I'm very, very interested in, and where we are doing a bit of work as well. I think if we can get to a situation where we have the relevant information of the collection encoded in a large language model or some other vehicle, but let's say it's a large language model, and we can ask that model, right? That's fantastic. That solves search, right? So if I, instead of saying, give me the right document, and then in that document, I'm looking for what I'm looking for, that's what we're doing, right? If I can tell the model, look, having read the collection, having memorized the collection, just answer my questions. Because all I wanted to know was find that quote for me, answer that, find that factoid for me, summarize these 5 documents that I otherwise painstakingly have to look for. So there's been an interesting white paper, gray paper, whatnot, by Google from last year, I believe, where they are doing a few experiments with that, with retrieval via large language models, by really memorizing the entire collection, pushing it into the parameters of the model, and trying to solve it that way. I think it scales very, very poorly, because they are looking at a few thousand or maybe 100,000 documents, so nothing at the scale of the web that we're thinking about. But there are interesting advances in that direction. So I'd be very, very excited to have something like this. And then in my world, where we try to support clinical decision making, this is something that I hope will sometime soon replace all this information extraction from EHR nodes, right, from electronic health records. I don't want to write a program and train it on data to find out who's a smoker in my data set and who isn't, and then find out who's an alcoholic in my data set and who isn't. If I can replace that with a model that understands the data well and memorizes it and then tells me who smokes, who's diabetic, or who whatnot, right? So I think there's going to be a lot of excitement there, but right now there are interesting engineering challenges to make it happen, and especially to scale. I think scale is the killer in this at the moment.
Of course, maybe the ChatGPT medical diagnostic tool will fall in love with my spouse and arrange to kill me by prescribing something.
Yeah, so you've been following Microsoft, and it's yes. Let's hope they're not building the next Tay again. You would have thought they learned. No, let's hope it doesn't kill us all.
Maybe support that. So I think there is no more questions, so I'll ask the last one. I think in the work you presented, if I understood correctly, you are modeling uncertainty at the score level, the relevancy scores, right? What about modeling uncertainty at the representation level? Like, for example, queries, some queries are ambiguous. Their representation there can be uncertainty in their representations.
Yeah.
Also the document side. What do you think about that?
No, I think this is key. So this is exactly what we do in this paper that I skipped over in the middle. So that's the 2021 paper, where we either at the query level or of the groups of queries level, where we average those query those query document pair distributions to get to this decay behavior, but really as an average of many either documents within the query or even many rankings. And I think this is really exciting. So we use this for query performance prediction or for tracking bias against or for certain queries or query types. But I think this really gives you, this is almost going to this instance versus system-wide behavior, because this really gets you more into the system-wide thinking of, oh, look, queries like these were either so poorly covered in your training data that you don't know what to do with them, or from a topical or phrasing way, or otherwise your model learned to bias against these, right? So this is something that I think is exciting in order to get our models more robust and to get really this understanding of where are the glaring black spots again in the model and in the ways that we train those. I have to say, so this was the 2021 paper, is a short paper. It was a bit crude around the edges, so we never really had the time to revisit this again, because we had this I think this vehicle in hindsight of the exponential distribution that we use to describe how fast uncertainty decays and how quickly you go from spiky to broad and murky, and all things are pretty much the same, is maybe not the best vehicle to do this. And I think that it would benefit from being revisited at some point to properly look at this. But definitely, I think there's a lot of gold, I guess, in looking at the whole result list or even aggregates over many result lists. So I would bet that you're on the money there.